Hello, everyone. Welcome back. We're back to lecture 6. In this lecture 6, we're going to talk about the Maxwell relations and the system properties. Maxwell relations are about the first and the second derivatives of the internal energy or free energies. So this is the combined law in terms of the internal energy equal to potential. So the YA here is the potential, and XA here is the molar quantity. So we know that the first derivative between the internal energy and the molar quantity is the conjugated potential. Now, if we make the derivative, another derivative between the potential and another molar quantity, non-conjugated molar quantity, we can go through this second derivative of the internal energy to the XA and XB, and then switch the order. We get XB to XA, then we get a YB to XA. So now you see that we switched the A and B, and switched the A and B at the bottom here. They are equal because they're equal to the second derivative of the internal energy. When we do experiments, the properties we usually measure are in terms of the derivatives of the molar quantity to its conjugated to the potentials. Is it conjugate or non-conjugate potentials? So if we inverse it, we get XB to YA derivative equals to XA to YB derivative. Okay, so what does that mean? So we can give an example. Between the volume and temperature, let's say volume is a molar quantity, temperature is a potential, but not its conjugated potential of the volume. So you could do S. So we have to here that we see these two. I conjugate is YA, XA. Okay, but then another side, we have the XB and the YB. Okay. So the very useful this one is because the left side, it's the chemical, usually we measure by experiments. At the right side, as we will talk about this class, we can calculate from the fundamental theories. So in addition to, except the internal energy, we can also use enthalpy to do the derivatives. But now in the enthalpy, we know that now we have a potential as the molar quantity. Okay, so we can now do the one between two potentials and between that potentials. Okay, so that's what we got. So we got the stress migration is chemical potential to the pressure derivative. Again, we can switch the order, as we can see here. We can go from this two to that two, different order, but they are equal because they are the same secondary derivatives of the enthalpy. Now we find that the potential derivative, the derivatives between two potentials would be equal to minus the derivative between their conjugated variables, molar quantities. In this case, it gets the partial volume. Now we can do another one between temperature and pressure. Okay? We call it the inverse thermal stress. So now we can see that now we get it's equal to the volume derivative to the entropy derivative, volume to entropy derivative. Okay. So this one is temperature to pressure derivative in a system. Okay, now we can move to next one. Is the Helmholtz energy. As we know that in Helmholtz energy, temperature, which is a potential, is one of the natural variables. Okay. Now that means we can do the pressure to temperature derivative. Of course, it's very similar to the temperature to pressure derivative, but just inverse. We can also do the temperature to chemical potential to temperature derivative. So this is called thermal diffusion. Is basically the chemical potential, the diffusion is driven by temperature gradient because the temperature affects the chemical potential. if we go through this Maxwell relation, we found it is equal to the partial entropy. The thermal diffusion is a Sorad effect or Sorad coefficient. And for this Maxwell relation, we see that it is equal to the minus the partial entropy of the component. We're going to discuss more in the future when we talk about the non-equilibrium system. Now we talk about the temperature to pressure derivative in the previous slide. Now we have the pressure to temperature derivative, which is the inverse of that one. It's called thermal stress. So the temperature affects the pressure value, and is related to the entropy derivative to the volume derivative. So again, has a minus sign. The next one is the Gibbs energy, but now Gibbs energy has two potentials as its natural variables. So that's the temperature and the pressure. We have done all of them before already, right? We did the chemical potential to pressure, chemical potential to temperature, we did temperature to pressure. So this is basically covered by the previous derivatives. However, we have to realize that the different derivatives are taking under different natural variables, capital constant, right? For the H, enthalpy, for the enthalpy, we have a entropy minus P and Ni, right? So these are the natural variables. If you have F, the natural variables would be T, V, and Ni. So it looks like the same derivative, mathematically formula, but the variables, capital constant, are different. Those are the natural variables. Of course, the reason we use Gibbs energy often is because the natural variables of Gibbs energy is what we control in experiments. Okay, so that's what I have: temperature, pressure, and a composition. We talked about the thermal diffusion before already. It's a partial entropy, and there's a stress migration. It's a partial volume. Now we also want to talk about the derivatives between chemical potentials. In that case, we defined another free energy. We call it general free energy. It's remove one of the potential, chemical potential, to be a natural variable. So now we have three potentials as natural variables now: temperature, pressure, and mu A. And the other components, we still have the molar quantity, moles, as the independent variable, as the natural variable. Now we get a new derivatives we didn't have before, as between the two chemical potentials. Okay. Now, of course, we can understand that if we change the chemical potential of one element, a component, the chemical potential of another component will be affected. But the effect of this interaction or this interdependence will be reflected by how the number of moles of the component will change. That's like it's basically chemical reaction, right? Or diffusion. Like we talk about the future uphill diffusion, because the diffusion of different elements interact with each other. Okay, now you put them together. There's a table. This table is between the derivatives of the potential and molar quantities. Okay. Now we generalize to all kinds of work. So we have temperature. Here we have a stress. And we have the electrical field and the magnetic field. Okay. So this is one we didn't show before, but we understand that there's three types of works it can be done. So the mechanical work, the electrical work, and the magnetic work. And then they have corresponding molar quantity would be the electrical displacement and the magnetic, or should be AL here. Okay. Now we immediately realize one thing is that the diagonal terms, I had them light, the red here, okay? And these are the derivatives between the conjugate variables. So they are always positive for a stable system. Okay, when the system to the edge of instability, it becomes equals 0. Okay. And also because of Maxwell relations, this matrix is symmetrical. So that means any quantity, these two are the same value. Okay, they are equal. And you take any two of them, So these two will be equal. Okay. So that's because we just showed before in this Maxwell relations. As I just mentioned, the diagonal terms, they are all positive for a stable system. But the off-diagonal terms is not required to be positive. So sometimes they are negative. Actually, there are many cases they are negative, like the negative thermal expansion. The volume decreases with increasing temperature. Okay, actually, all of them can be negative at a given condition or different systems at different conditions. And the last row, this parameters we just discussed it, is between the two potentials. Okay, not between the moles here. Okay, so these are the new quantities, which not discussed very much. They are the chemical reaction driven by different potentials. This table shows the quantities between derivatives between two potentials. Okay, between two potentials, and is equal to minus between the two molar quantity derivatives between the two molar quantities. And those are the new quantities. Okay, very rarely discussed in the literature, though Gibbs discussed it in his papers in 1870s. Again, this is a matrix. The table is symmetrical because the Maxwell relation, as we showed before. The off-diagonal terms, because the diagonal term is 1, the off-diagonal terms, quantities there can be negative or positive. Okay, can be negative or positive. So sometimes in the literature, people say, oh, I got a surprising new property. It's not really surprising if you look at the fundamental thermodynamics. They are just naturally come out from the Maxwell relation. The symmetrical, and also it's not required to be positive by the stability of the system, as we will discuss in the future. Okay, so that's the end of lecture 6. I hope you enjoyed. Please share your comments on YouTube, and see you next time.